Okay, so welcome to the Extreme Universe Colloquium. Today we are very happy to have Professor Suvrat Raju from ICTS. And before we start, let me introduce Suvrat to the people who don't know. So Professor Raju, who get undergrad in Delhi University in 2002, and he get PhD in Harvard, I think 2008. After that, he did a postdoc in HRI, the famous institute in India, till 2012. And after that, he becomes a faculty in the ICTS, International Center for Theoretical Physics, International Center for Theoretical Science, sorry, TIFR. And then now he's promoted, and from 2022, he's a full professor. He's very well known for his many significant contributions to the theoretical physics, especially quantum gravity, black hole physics. And one of the most famous proposal of him is so-called the Papadodimas-Raju proposal, which is one way to see the behind the horizon of the black hole through the entanglement structure. He's recognized as a world leader of his generation, and he gets several prizes, including the Nishina Asia Award from Nishina Memorial Foundation in 2022, and also from ICTP Trieste, he gets the ICTP prize in 2019. So today we are very much excited to hear from Suvrat about recent development of the quantum gravity. So everybody, please welcome Suvrat. So Suvrat, it's up to you.
Thank you very much, Nori, for that very kind introduction. Thank you, all of you, for coming for this talk. I'm going to speak today about this question on how is information or how is quantum information localized in quantum gravity. And I'll try and explain to you in this colloquium that this is a very interesting question with a rather unexpected answer in some situations. Before I go on to my colloquium, I always like to start by acknowledging my collaborators because I'm going to speak about work done in collaboration with many excellent researchers. Some of the most, this is the work I'm about to present is part of a long-standing program going back several years. Some of the most recent papers we wrote in this were last year with Joydeep, who was a former student at ICTS and now a postdoc, Priyadarshi and Tunir, who are students at ICTS, soon to be postdocs, and Victor, who was a postdoc at ICTS, now at CISA. Some of it goes back earlier to work with Alok Ladda from Chennai Mathematical Institute, Siddharth, who was a postdoc at ICTS, Pushkal, who was a student at ICTS, Chandramouli, who was a student at ICTS, and Olga, who was a postdoc at PI. And also some of it is related to work that we did with a large collaboration we sometimes call the Group of Seven, which is Hao, Andreas, Carlos, Lisa, Marcos, and Sanjeev. And in fact, as Nori mentioned, some of these ideas go back even further to work that we did with Kyriakos now more than 10 years ago. So I wanted to acknowledge this work because it's all joint work with all of these authors. Okay, so let me now start by addressing the question that this colloquium is about. So this question is about, the colloquium is about how is quantum information localized in a theory of quantum gravity. Before I address that question, I would like to spend a few minutes trying to remind you of, how quantum information is localized in a non-gravitational theory. So in a non-gravitational theory, the kind of configuration that I want to look at and compare with quantum gravity is a configuration of the kind that appears on the screen, where you have some non-gravitational theory, maybe there's a lattice regularization of the theory, and there's a pink region, which is a bounded region, and there's a yellow region, which is the complement of the pink region. And the main point I want to emphasize, which is a very, very simple point, it's so simple that we sometimes don't even think about it, is that the state of the degrees of freedom inside the pink region can be specified independently of the state of the degrees of freedom in the yellow region. So, if I looked at the left picture and looked at the right picture, if you look, you'll see that this qubit has been flipped from being up to down. This qubit outside has been flipped from being up to down. But there was nothing that said I had to do both those operations simultaneously. I could do one operation or the other or both or neither. Right? So there is no constraint that relates what the degrees of freedom outside do compared to what the degrees of freedom inside do. This very basic property of non-gravitational theories is rather key to our idea about how information is localized. So when we look at information on a spatial slice, so I want to emphasize that in this talk, I'll often draw these pictures But these are always pictures of a spatial slice or a Cauchy slice. Okay, they're snapshots at one instant of time. When we look at a snapshot of a non-gravitational theory of a state, what this cartoon shows is that we can prepare a state which looks exactly like the vacuum outside this region, but it has some excitation inside this region. And an observer here cannot really do anything to determine whether, to know that they're not in the vacuum. Of course, if they wait for some time and light eventually from here will reach outside, but at this instant of time by the detectors, all experiments they do look exactly like the vacuum. And what is more, you can change the form of the excitation inside without changing anything outside. And so this is what leads us to a usual picture that information is localized inside some region, and it is not available in the complement of that region. So this is just very usual. It's our mundane notions of how information is localized. I'm going to try and tell you that in a theory of gravity, the picture is somewhat different. In particular, contrasting it with the cartoon that I just showed previously, I'll try and persuade you that first of all, you cannot even set up a state of this kind where you have an excitation inside some bounded region and it looks like the vacuum outside. So in theory of gravity, if you set up an excitation in some region, there's some traces that you have left outside. Now, this should not be so surprising because this is also true in a classical theory of gravity. You put some excitation in a region, you can measure its mass outside. But I'm going to try and make a stronger statement in this talk. And the stronger statement is that in a classical theory of gravity, you can sometimes reorient the mass in a region in such a way so as to leave all observables outside changed. But what I'm going to tell you in this talk is that in a theory of quantum gravity, if you correctly take into account both quantum mechanical and gravitational effects, if you change the form of the excitation in this region, in this bounded region, you're forced to also change the form of the some observables outside. And so an observer outside can always determine what's happening inside this region. So this is the broad story of what I'm going to tell you. And of course, I'll make it more precise and give you evidence and various aspects of this proposal as we go along. This is an overview of the main points I want to make in this talk. The first point I want to make is that this unusual localization of information can be inferred from a gravitational analysis, provided one makes some careful assumptions about the UV complete theory that I'll outline. However, this is not just some formal statement about gravity. Rather, if one looks at simple states, perturbative states, one can see signs of this effect even in perturbation theory. So it's really something that's very physical. I also want to tell you that this effect is important for the black hole information problem. On the other hand, I'll also explain in some regimes, this effect is not important. And in those regimes, gravity behaves like an ordinary quantum field theory. So I'll also tell you about that. And the last thing I want to say is that all the results that we have, they pertain to information. And of course, they'll remind you of famous dualities that we have in string theory, these holographic dualities that say that if you have some degrees of freedom in a region, you can describe them by a dual theory on the boundary. But the results that I'll describe in this talk pertain to information and not to full dynamical holographic dualities. And that's why we call this effect the holography of information, rather than just calling it full-scale holography. Okay, so let me start with something very simple. And I want to start by giving you some intuition, and then I'll give you more precise arguments. So the first question that you could ask is, from a physical point of view, why should one even believe that gravity has this unusual property of localizing information differently? So I'm going to give you some simple physical arguments, and then I'll give you a more formal argument. Okay, so for now, I just want to give you simple intuition. Let me remind you of a very basic property of quantum mechanics. A very basic property of quantum mechanics is that quantum mechanics obeys an uncertainty principle. Of course, uncertainty is between momentum space and position space. However, in a relativistic theory, momentum comes together with energy necessarily. And so, the uncertainty principle tells us, if you take some state and you sharply localize its energy, like is shown on the right, so the energy spectrum is sharply localized, then that excitation that you have is something that is necessarily delocalized in position space. Now, this is something that's familiar to us. It's taught to us, when we first learn about quantum mechanics. And of course, this by itself is not an obstacle to localizing excitations in a bounded region. And how do we do that? Well, we do that just by superposing different energy eigenstates. So I take one energy eigenstate, I add to it another energy eigenstate with some phase, a third energy eigenstate with a third phase, and so on. In fact, you can check you have to superpose always an infinite number of energy eigenstates. But if you do that with the right phases, you can get a wave function that's strictly localized in position space, okay? Of the kind that we have on the right-hand side. And this is also something that we learn when we study quantum mechanics usually. So now the question is, what is different about gravity? Now, what I want to tell you is that what is different about gravity is also a very basic principle of gravity, which is the Gauss law. And the Gauss law, in fact, is simply the statement that if you have some bounded, you have some energy, this energy can always be measured at infinity. And the expression we have on the screen is the famous ADM Hamiltonian in general relativity. But if you haven't seen this, it doesn't matter. This is just the Gauss law. It just tells you, you look at the integral of the gravitational flux at infinity, and that will tell you the energy inside some region. In fact, in the modern theory of gravity, in general relativity, this is the definition of energy. This is the good definition of energy. And we don't have other good local definitions of energy, except in some special cases. And we really define the energy by looking at the gravitational flux at infinity. So this is also a familiar property of physics about gravity. But now I want you to think of what happens when you put together this basic property of gravity with the quantum mechanical property that I just mentioned. Okay? So now see that in a theory of quantum gravity, when you have some excitation, and this is the excitation with a cartoon with a sharply peaked energy, this excitation cannot live on its own. It has to come with a gravitational field. And the gravitational field has to have a certain property, which is that its integrated flux at infinity should tell you the energy of the excitation. So you cannot just think of an excitation of some matter or even a graviton just by itself. There's a constrained part of the state which is related to what the gravitational field at infinity is doing. And the main physics of what I'm about to say is that if you now try to play the game that you played for a non-gravitational theory, which is you superpose different energy eigenstates. However, now you find that you can't just superpose this wave function of this matter part, but you also have to superpose, the gravitational field. Each of them comes together with the gravitational field. And the main physics is that these gravitational tails, they prevent you from arranging for destructive interference outside a bounded region and constructive interference inside a region. And it's important that it's not just the total energy, but rather correlation functions of the energy and other observables that carry information about the state. What I told you right now is, of course, not a proof of the statement, but it might suggest to you that even based on very basic physical principles, just putting together basic principles of quantum mechanics and gravity, one might suspect that gravity localizes information somewhat differently from non-gravitational theories.
Suvrat, if you don't mind, can you just expand the explanation with the tail prevent destructive interference? Yeah. I missed the point. Yes, please.
Yeah. So so imagine that you have some theory of gravity coupled to some matter. And we want to write down a wave function that has the property that it differs from the vacuum in one region and coincides with the vacuum everywhere else. Mm-hmm. However, the way we were doing that in a non-gravitational theory was we were superposing different wave functions.
Yes.
Mm-hmm. So it has to have constructive interference inside and destructive interference outside. Mm-hmm. However, now when you try to superpose this wave function, there is also the gravitational field which extends out to infinity. Mm-hmm. So you have to arrange for destructive interference, not only of this part of the wave function, the left-hand side, which is the part you were originally superposing, but also of the gravitational field. But you see, the gravitational field has different energy eigenvalues for each of these different cases. Mm-hmm. So you cannot arrange for destructive interference of the gravitational field and of other matter degree and of other parts of the wave function outside a bounded region and have constructive interference inside. What I said right now is not a proof, but I'm just pointing out that you can see that because you have, every wave function with a given energy has to be dressed with, gravitational degree of freedom. Arranging for this destructive interference is much harder than it was in the non-gravitational case. And in fact, the argument is it's not possible. This is just some intuition for what the physics is.
But just to make sure, but what Gauss law tell you is it's energy. Am I right?
Yeah.
It's only energy.
That's right. The Gauss law tells you the energy, but the Gauss law tells you that every state you have, every time you think of a wave function with a given energy, there has to be an accompanying gravitational field, which has the property that the flux of the gravitational field at infinity is related to the energy.
Yeah. Okay.
So you see the two parts that go in here are the Gauss law, which tells you that you have to have both of these together, and the uncertainty principle that tells you have to now superpose these different energy eigenstates. Okay. And so that's the basic physics of what I want you to keep in mind. I'll give you a sharp, clearer argument as we go forward. But yeah.
Okay. Thank you.
Thank you. Okay, so let me now tell you what the precise results are. So far, I've just been showing you cartoon pictures. Of course, I need to say something more precise. And I'll tell you now what the precise results are. And for the experts in the audience, I'll also give you a proof. And then I'll go back and discuss other aspects of these results. So here are the precise results we have for asymptotically flat space. In asymptotically flat space, the result is as follows. Think this is the so-called Penrose diagram of asymptotically flat space. So this region is called null infinity. This is simply, you take flat space and you kind of do a coordinate transformation so as to bring infinity out to a finite region. And when you do that, you find there's a region where all future light rays reach, and that's called null infinity. That's this region on top. There's a part from where all light rays emerge, and that's past null infinity. In a non-gravitational theory, we can think of the set of all observables as Cry plus, which is a name for null infinity. And, the set of all observables, which is sometimes called the algebra of observables, has the property that it comprises independent operators on different points of null infinity. These operators in particular are labeled by a coordinate that runs along null infinity that's called the retarded time. And there are different kinds of degrees of freedom that live on null infinity, always massless degrees of freedom. And you can think of, these operators at null infinity at various values of the retarded time, and they're all independent operators. The result is that in a theory of gravity, any operator on this algebra on null infinity can be approximated arbitrarily well by looking at operators that live in retarded time minus infinity to minus 1 over epsilon. On the cartoon picture, the semi-infinite interval, in fact, just looks like the small red band that you have here. So the statement is that all observables in all of this cone can in fact be approximated arbitrarily well by observables in this little red band. There's, of course, a similar statement for past null infinity, which is all observables in the blue cone can be approximated arbitrarily well by observables in the orange band. There's a result for ADS, and in ADS, the statement is, if one thinks of a non-gravitational theory, there's an algebra of observables. The algebra of observables lives on the entire boundary of anti-de Sitter space. This boundary, in this case, is a time-like boundary. So the observables are labeled by different values of time. In a theory of gravity, any asymptotic operator can be approximated arbitrarily well by observables from the small time band that lives in a band from 0 to epsilon. Of course, if you look at this, you will see that this is very reminiscent of the famous ADS-CFT proposal. However, this result, as I'll try and explain, does not involve invoking ADS-CFT, although, of course, it's consistent with ADS-CFT. We also have a result for the case of the positive cosmological constant, and that result is as follows. If you think of a spacetime that's asymptotically de Sitter spacetime, and in this spacetime, this is a cartoon of such a spacetime, then we look at the future boundary of that spacetime, and a full set of observables in a non-gravitational theory corresponds to correlation functions on this future boundary at different values of the coordinates. It turns out that in a gravitational theory, if you look at any open set of this future boundary, and you look at correlation functions, which one needs to specify carefully, and I'll say a little bit more about that, then that is a complete set of observables. So you look at correlators on any part, any small open region of the future boundary, that's enough to determine correlators everywhere on the future boundary. Okay. So the precise results that I just showed you, and I'll give you some more evidence for them, they're always in terms of asymptotic algebras. You will notice that I always was making reference to infinity. But physically, these results, basically tell you that all information about the state that you would usually specify on a full Cauchy slice is available in a subregion. So this is the precise result. We make it infinity because that's where you can say precise things about gravity. But if you think of the picture of what I said, the picture is that in flat space, you think of a Cauchy slice. And in a non-gravitational theory, you would specify the wave function in the whole slice. But in the theory of gravity, observables on this dark red band are enough to determine everything in the bulk. Similarly, in ADS, in a non-gravitational theory, you would specify observables on a full Cauchy slice. But in a gravitational theory, observables near the boundary of the Cauchy slice are sufficient to determine all information. In de Sitter space, again, you would specify observables on the full Cauchy slice. This Cauchy slice in de Sitter space, I emphasize, doesn't have a boundary, unlike the case of ADS and flat space. But here the result is that if you look at any open set on this Cauchy slice, that set of observables is complete. You might also think that the results in ADS and flat space are kind of different. In ADS and flat space, I was saying that the boundary of a Cauchy slice has information about the whole. But in de Sitter space, I was saying something else. Any open set has information about the whole. In fact, you can put these results on the same footing by saying the following. The complement of a bounded region of a Cauchy slice always has all information about a state. In ADS and flat space, notice this reduces to what I said, because a bounded region is a region of this kind that doesn't extend to infinity. And so the complement of a bounded region always includes the part near infinity. However, in de Sitter space, the Cauchy slices are topologically S3s. And therefore, every little region, every open region is in fact the complement of a bounded region. And so while it's true the purple region is the complement of the blue region is also the complement of a bounded region. And that is why, there's a common perspective that tells you that all of these three results, which are some precise results, can be combined with this slogan, which is that the complement of a bounded region has all information about the state. Okay, those were the results. I now want to tell you what are the arguments that lead to those results. How do we arrive at these results? So I'll explain this quickly, just to give you a sense or a flavor of what we need to do to obtain these results. If you'd like more details, I'm of course happy to give you these details. These results that I just presented, they rely on some assumptions that we need to make about the full UV complete theory of quantum gravity. In particular, here is how we derive the results for flat space. For flat space, we need to assume that the asymptotic algebra at null infinity is well defined in the full theory. We need to assume that the Gauss law holds, and more precisely, that the vacuum can be identified by charges near the pass boundary of future null infinity in the full theory. And finally, that the Hamiltonian is bounded below in the full theory. These are all, as you will notice, very reasonable assumptions we might want to make about a UV complete theory of quantum gravity. But of course, since we do not understand what UV complete theories of quantum gravity should be in four-dimensional flat space, these are assumptions that we have to make and are not things we can prove from first principles. Let me tell you now how these assumptions lead to the result that all operators on null infinity can be approximated near the pass boundary of null infinity, which is denoted by scri plus minus. Okay, so the first assumption I made was that the asymptotic algebra makes sense in the UV theory. That tells you that it makes, even if in the bulk you have all sorts of complicated degrees of freedom. We know in string theory we have all sorts of complicated degrees of freedom. There are branes, and the language of quantum field theory is not a good language to use in the bulk. The assumption is that at infinity we can still speak of the familiar degrees of freedom that we have. This is true, for instance, in string theory, where we still speak of an S matrix, right? And so we still say that at infinity, there's some notion where all excitations become far separated, where we can speak of the usual algebra of observables. And if we do that, then we can also think of what the Hilbert space of the theory is. And the Hilbert space of the theory is obtained by basically acting with this asymptotic algebra of observables, which lives on null infinity and is labeled by this retarded time u that runs from minus infinity here to plus infinity, acting on the vacuum. This is, in fact, the standard way in which we generate the out space for the S matrix. So this is not a new construction. It's just what we call the out space. You take operators at infinity, act on the vacuum. That space is called the out space. Now I want to think of a subalgebra of the set of observables at infinity, which I'll call A minus infinity, which consists of these same observables at null infinity, but now restricted to this time band from minus infinity to minus 1 over epsilon. So that's just a definition. I'll tell you where it appears. Okay? The next assumption I said we needed to make was that the Hamiltonian is bounded below. If one makes this assumption, then with some further arguments that have to do with the analytic properties of correlation functions, one can prove that any state in this Hilbert space that I just described, the out space, can be obtained by acting with an element of this subalgebra on the vacuum. Let me emphasize that the Hilbert space was originally defined by saying I act with all operators on null infinity on the vacuum. But if the Hamiltonian is positive, or if it's just bounded below, you can show that you would get the same Hilbert space, or at least you'd get another Hilbert space that was dense in the original space, simply by acting with elements of the subalgebra on the vacuum. Now, the thing that's special to gravity, so far I didn't use anything about gravity, was that the vacuum of the theory can be identified by an operator at infinity. This, in fact, is exactly the Gauss law that I said previously. You see, the Gauss law tells you can measure the energy, but the energy is a quantum mechanical observable. So when you measure the energy, the basic rules of quantum mechanics tell you what you're really measuring are the expectation values of various projectors onto eigenstates of the energy. So say you measure the energy in some state, you can then ask, what is the probability that you get 0? That probability is given by the expectation value of the projector on the vacuum of the theory. In an ordinary non-gravitational theory, measuring the energy requires you to make a measurement on the full Cauchy slice in the bulk. But in a theory of gravity, you can measure the energy at infinity, and therefore in a theory of gravity and only in a theory of gravity, the projector onto the vacuum is an element of this subalgebra that lives at infinity. If you now put these arguments together, you see that any element of this Hilbert space, you can of course expand in a complete basis of states. This requires this assumption that the algebra makes sense at infinity. You can define this out space. But now the assumption that the Hamiltonian was bounded below tells you can write every element of this state as an action of the subalgebra on the vacuum. Until this step, everything would also be true in a non-gravitational theory. However, in a theory of gravity, this operator that appears in the middle, which looks like bra 0, ket 0, ket 0, bra 0, can be replaced by the projector in the vacuum, which is also an element of this subalgebra at near u equal to minus infinity. And therefore, you see that any operator in the theory can be approximated arbitrarily well by an operator near the past boundary of future null infinity. I went through this proof somewhat fast, and of course, I didn't give you all details, but I hope this makes clear what are the kinds of assumptions and what are the kinds of arguments that lead to this result.
So, Suvrat, do you mind I ask some couple of basic questions?
Yeah,
so you say we know there's Gauss law, and
Yes.
then how does a Gauss law allow you go from step 2 to step 3? Meaning that by the Gauss law, where you measure the energy, you say we know P0. Is that what you say?
No, it's the fact that P0 is an element of the algebra at infinity.
Yes.
You see, because step 2 to step 3 is just P0, but in a theory of gravity, P0 is an element of the algebra at infinity. Xn is an element of the algebra at infinity. Xm is an element of the algebra at infinity.
Yes.
So what you have here is a sum of a product of elements of the algebra. And because the algebra is closed under linear combinations and products, the whole right-hand side becomes an element of the algebra A minus infinity. In a non-gravitational theory, P0 is not an element of A minus infinity. So this, you can always do up to step 2 in a non-gravitational theory. But this does not tell you that the operator A is an element of A minus infinity.
So you claim that P0 is an element of the operator, is a nature of the gravity. Is that what you claim?
Yes. So maybe I don't know if I can annotate this screen. Yeah, I think I can annotate. So P0 is an element of A minus infinity. This is a property of gravity.
Okay.
So you see, so that tells you this is an element of A minus infinity.
Uh-huh.
This is an element of A minus infinity. For this, I require the positivity of the Hamiltonian. This is an element of A minus infinity. Therefore, the whole operator is now an element of A minus infinity. The fact that the energy can be measured in this little red region, this is only true in a theory of gravity. In any other theory, the energy is a bulk observable. It's not a boundary observable. So the fact that the energy is a boundary observable is what lets you argue that the whole operator A, this is an arbitrary operator, is in fact an element of this algebra at minus infinity.
So you say that in the theory of the gravity, due to the Gauss law, you can detect what is a vacuum state, assuming that the Hamiltonian is lower bounded by below.
Yes.
Therefore, you can detect the vacuum in gravity due to the Gauss law. Therefore, you can detect what is a P0 in the theory of the gravity only.
That's right. Exactly.
Oh.
Exactly. Now, P0 is... Yeah.
I mean, but in order to measure the vacuum state, you need precise measurement of the energy coming from the Gauss law. Am I right?
Yes, that is correct.
If you have very short time scale, how do you measure so precisely due to the uncertainty?
Okay, so this is a good question. We can ask this question about how hard or how easy it is to make these measurements. So first of all, I want to emphasize this is not actually a short time scale. It's minus infinity to minus 1 over epsilon. It looks short on the Penrose diagram, but it's actually a semi-infinite interval, this red region.
So you claim that up to the amount you want to make it precise, you have enough time to measure precisely about the
You have enough time. As an operator, it's well defined. But then you can ask, physically, what what if I'll restrict the precision with which I can make observations? And I'll say that a little later when we come to that. But for now, just as an observable, it's well defined. There's no problem as a formal observable, it's well defined. So this is what I proved right now, some formal property of operator algebras. And then you can ask, can you really see this in if you had some experiment? And I'll say a little bit more about that.
Okay, thank you.
Okay, thank you.
Sorry, can I ask a question?
Yes, please. Yeah.
So in classical gravity, there is no Hamilton is not bounded below, and he usually Hamilton is not bounded below.
Even in a classical theory of gravity, I would imagine the Hamiltonian is bounded below. There's positivity of Hamiltonian. The thing that would fail in a classical theory is the second step. This step required entanglement. It crucially requires entanglement.
Okay.
Or the uncertainty. I'm trying to annotate again. Now I can't annotate.
I see.
Yeah, this step would fail in a classical theory.
I'm wondering. Because Gauss law is coming from the classical gravity, not quantum gravity. So here you use it. So.
Of course, I'm using it in a quantum mechanical sense because you see, the Gauss law classically would tell you can measure the expectation value of the energy.
Right.
I want to do more. I want to measure the probability that you get to zero. So it's a quantum mechanical observable that I'm measuring. You see, if I could only measure the expectation value of the energy, which is what you could do in the classical theory, this argument would not go through. It's important that I'm using the Gauss law in a quantum mechanical sense, in that I'm saying that if you measure the energy, you get a probability for getting different answers. And P0 tells you the probability that you would get zero.
So sorry, because quantum gravity is non-local in a sense. So quantum gravity will be non-local. So maybe the Gauss law, we use a classical notion of the geometry.
Well, I don't know what you mean by saying quantum gravity is non-local. What does that mean?
Non-local means maybe a quantum gravity, there is no strict notion of the bulk geometry, but Gauss law means assuming such a notion.
Yeah, thank you. You see, the point is that in the bulk geometry, you're right. There might be no strict notion of the bulk geometry. That's why I needed to make this assumption one, which is that the asymptotic algebra makes sense in the full quantum theory. So notice that everything I said, and this is in fact key to the point, was always defined at null infinity. So you're absolutely right. In the bulk, you might have a black hole, or you might have a fluctuating space-time or something. However, even in quantum gravity, we hold the asymptotics fixed. So for instance, when we discuss ADS CFT, we say the asymptotics at ADS at infinity is fixed. And so this is in fact exactly the reason why this whole argument is made at null infinity, because in the bulk, as you say, you could have fluctuating space-time. But at the structure of null infinity and the algebra at null infinity, we think should be stable, even in a theory of quantum gravity. So that's why this argument is made at infinity, to address the point that you just made.
And Gauss law means you assume such things energy conservation, something like that.
Gauss law means that the energy is an observable near the past boundary of future null infinity. So you see, you forget about the slice through the middle. The structure of null infinity is stable. In a non-gravitational theory, the Hamiltonian is an observable, but it's an observable on all of null infinity. In a theory of gravity, the observable is the Hamiltonian is an observable near the past boundary of future null infinity. So it's always a statement about the asymptotic geometry, and the Gauss law is meaningful even for the asymptotic geometry. It tells you that the Hamiltonian, a theory of gravity, is an observable only here. You don't need to make a measurement on all of null infinity.
Thank you.
Thank you very much for the questions.
Can I ask a question?
Yes, please. Yeah.
In the case of gauge theory, for example, U1 gauge theory, it is not gravitational, but it has a Gauss law. So I think it makes a difference that gauge charge is not does not appear in the uncertainty relation, but the energy does. Is it correct?
Yes, this is correct. And notice that, in gravity, we have something more. You can project onto a vacuum. So if you believe that the vacuum is unique, you can project onto a unique state from infinity. That's what this projector is doing. In a gauge theory, because of what you said, there are various ways to say it, and the fact that the charge is both positive and negative, you can never project onto a vacuum. You always project onto an infinite dimensional manifold. So if I project, for instance, onto the set of states of zero charge, that's never a unique state. In fact, it's an infinite dimensional manifold of states. So the fact that the energy is positive and the charge is not positive leads to this. It's also related to what you said, that the uncertainty principle involves energy and not charge. I mean, these statements are all related.
I see. Thank you.
Thank you. Okay. Are there questions or should I go on? Okay, this previous analysis I made was an argument at null infinity. So it tells you the algebra at null infinity can be squeezed down to the algebra near the past boundary. In fact, this algebra does not account for excitations of massive particles. So massive particles go from past infinity to future infinity. They never reach null infinity. And in fact, we don't have a satisfactory asymptotic description of massive fields at Scri plus or Scri minus. However, we've made some progress by studying massive particles at I0. This is some forthcoming work with other collaborators, Anupam, Chathira, and Priyadarshi, which we might have something to say about. But I want to note that for now, there isn't a clear description of clear proposal for how to extend the previous result to also include massive particles. Okay. A similar argument of the kind that I made in flat space implies that all observables on the boundary of ADS can be represented in a small time band. In ADS, there's no subtlety with massive particles. I emphasize this is consistent with ADS-CFT. In fact, ADS-CFT tells us if you take a single time slice, that is sufficient to obtain all observables. But the argument that we have does not assume ADS-CFT, although it's consistent with ADS-CFT. Rather, it makes the other assumptions we wanted to make about the theory of gravity that I described earlier. So it gives us an explanation for why gravitational theories are holographic, but non-gravitational theories are not. Yes, please.
Yeah. So I agree that your argument in principle says that without ADS-CFT, but you assume that Hamiltonian is bounded below, is that right?
Yes.
And it's well known that gravitational action has no upper or lower bound. So without holography, it's not clear to me how do you justify the assumption that Hamiltonian is bounded below.
Yeah, I mean, the action, by the way, not having a bound, I mean, that might be slightly different from the energy not having a bound.
Yeah,
because
I completely agree with that. But
the positivity of energy.
It's very non-trivial assumption you made.
Yeah, it's an assumption. You're right. We have to assume that the energy is bounded below. You're right. And we don't have a proof for that. Of course, in classical theory, there are all these positive energy theorems. There are these proofs of positivity of energy. But you're absolutely right. We need to make some assumptions about the UV complete theory of gravity, which we can't justify, I mean, in some first principles way. But it's saying, if we believe it, I think it's a reasonable assumption that the energy Hamiltonian should be bounded below. And if we make the assumption we reach this argument, of course, it's possible that it's linked.
Right. Thank you.
Okay, as I said, there's also an argument we can make in de Sitter space. I don't want to go through the argument in detail, but I just want to give you a flavor. The flavor is, the argument in de Sitter space goes in a slightly different way. Once again, we have to analyze the constraints that come on the wave function due to gravity, which is the Gauss law that I mentioned. And these constraints, which are called the Wheeler-DeWitt equation, they force the wave function of the universe at late times to take a particular form, look like a phase factor times the partition function of a conformal field theory. The form is not important. I just want to emphasize that the constraints force the wave function to take some form. And in that form, it so happens that all allowed wave functions have the property that they are scale invariant. And because they're scale invariant, if you measure cosmological correlators in some open region of the late time slice, these cosmological correlators you have to define carefully because you have to define observables in quantum gravity carefully. We can define them by means of some gauge fixing procedure. If you define these observables, which are gauge fixed, and then they correspond to insertions of fields at some late time, in all these states which are allowed by the gravitational constraints, it turns out that these observables have the property that they are scale invariant. And because they're scale invariant, if you give me observables in this little region, I can scale them out of the region and get observables everywhere. So that's just a sense of how the flavor of the argument goes in de Sitter space, which leads us to the conclusion that if you give us these cosmological correlators in this open region, that's sufficient to determine them everywhere. It would be nice to have, even in de Sitter space, a more universal argument of the kind that I gave you in flat space and anti-de Sitter space, but we don't have that yet. Rather, we have something that arrives at this result using a rather different flavor of analysis. Okay, so that's what I wanted to say about holography of information. Now, in the remaining 15 or 20 minutes, I want to discuss some aspects of this result. I want to discuss first a result in which this is perturbative. It's related to Nori's question about, when can you measure these things? I want to discuss a place where, this is not important, and then I want to spend some time discussing the case of black holes. Okay. So let's ask, I proved some result about operator algebras, and you might worry, at some result about operator algebras, is it really something that's physical? So here's a physical example that I want to give that I think is very illuminating. Imagine the following case. This is once again flat space, and I have thought of an excitation that hits in flat space that comes and hits the boundary of flat space somewhere in the middle. Okay, so this is some excitation that comes and hits null infinity in the middle of null infinity, and we have some observers who live here who have some detectors which are only allowed to turn on near the past boundary of future null infinity, which is this red region here. And we ask these detectors to determine the profile of this excitation as it comes and hits null infinity at this point here. Now, in a theory without gravity, this is of course impossible because if these observers, they wait and may make measurements in this blue region, then of course they can determine it. But from this red region, there's no way they can determine what's happening here. Okay, so the challenge is, can you use quantum correlators near Scri plus minus to determine what the form of this excitation is, which in this case is given by this function f. So the excitation is just a unitary operator. You take some operator null infinity, smear it with this function f, act on the vacuum. Okay? And the challenge is these people have to make some measurements here and determine what f is. In fact, the answer is quite simple. What these observers need to do is measure the correlator of the energy with other observables. As you see, again, the energy is very important. It's a simple calculation of this 2-point function. If you do it to order lambda, lambda was the parameter that went into the unitary, you will find the following answer. You will find that even though this unitary, this function f had support only between 0 to 1, this 2-point function of the energy and another observable inserted at a value u has support even when u is in this region minus infinity to minus 1 over epsilon. In fact, if you're given the function f convoluted with this Green's function, you can completely determine f just by expanding it in powers of u. So if you know this answer on the right-hand side for u near minus infinity, you expand it in powers of u, you get all the moments of f, and using that, you can completely reconstruct f. So you see, this is a concrete physical example of how this effect that I'm speaking of is not just some formal effect, but rather it's something that for simple states, this was a very simple state, you can actually, do concretely by just computing these simple correlation functions. This example is very instructive. In fact, it helps to answer some of the other questions that were asked. For instance, you could ask, where did gravity enter? Of course, this idea cannot work without gravity. Gravity entered because you measured a correlator of the energy and other observables. In the absence of gravity, you have exactly local gauge invariant bulk operators. So the vacuum and the vacuum with this unitary operator, which is just e to the I trace of f squared, cannot be distinguished from each other because this unitary operator commutes with all observations that these observers make because it's space-like separated to them. So you see that the gravity is very important, and gauge theories do not have this property of being holographic. You could also say, how, you are measuring the energy, but what if you had two excitations which had exactly the same, energy? So maybe theories of gravity don't have global symmetries, but just to make life harder, let's imagine that we do have two fields which are related by global symmetry. We call them O1 and O2. And then I create an excitation, which is the blue excitation with O1 and a green excitation with O2. And then you can ask these observers, can they distinguish between the blue and the green excitation? And the answer is yes, because they can measure correlators of the energy at infinity with the field O1 and correlators of the energy at infinity with the field O2. And these correlators are different in these states. And so they'll distinguish between these states. And so I emphasize it's important, the point I want to make here, is that it is not just a measurement of the energy. Rather, it's quantum mechanical correlators of the energy with other fields that have the information that we are looking for.
So maybe this is important, so let me ask. So you claim that not only the energy, but O1 and O2 are different operator, is that what you say?
Yes. So
then
O1
you
and
need
O2
all
are
the
some
correlator. You need all the correlator information.
That's right.
Then you can do it. Is that what
That's right. That's right. So these two states have exactly the same energy because I'm assuming O1, O2 are identical fields. They're related by global symmetry. So not just the energy, but rather, you have to measure this 2-point function. And so it's important that, just gravitational degrees of freedom don't have all information.
Yes. Thank you.
Okay. Okay, now, maybe some of you were thinking about this question, which is, all this was happening in the linearized theory. So there was no complicated non-local dynamics, even if gravity does have non-local dynamics quantum mechanically. How could it be that these observers here, these observers here had information about what was happening in something that was space-like separated to them? This is an important physical point. And you see, the important point is that in a theory of gravity, you cannot just set off an explosion in this middle here. That is inconsistent with local energy momentum conservation. Rather, I was kind of not drawing the complete picture. And the complete picture, in fact, is that this excitation had to come from past null infinity. Right? So the true statement is that in a theory without gravity, it is possible to send the excitation from Scri minus in such a way that no traces remain outside. So it's possible to send excitation into a region so that no traces remain outside. But in the theory of gravity, when you send excitation inside, some effect always remains outside. And if you pick up that effect carefully, you can determine what it is that's inside. So this is not inconsistent with causality in any way. It's really a failure of this split property, which is a property you can prepare a state by sending in information from outside and erasing all traces outside. And that is something you cannot do in a theory of gravity. This will be important again when I say some things about black holes. Okay, now I want to say a little bit about when these effects are not important. Okay, so of course, it's not the case that these effects are always important. One example where these effects are not important, in fact, is the famous case that we study a lot, which is entanglement wedges in ADS-CFT, which is the case where the Ryu-Takenagi formula applies. Imagine that we think this is a picture in ADS of a Cauchy slice, and we have a region R, and we have a region R bar, and these regions both extend to infinity. Remember, when we think in ADS and we think of these regions entanglement wedges, ordinary entanglement wedges always extend to some part of the asymptotic region. And then it's clear that you cannot determine what's happening in R by making measurements in R bar. Physically, you see all the arguments I was giving previously will break down because you can't measure the total energy inside R from R bar. There's no Gauss law that tells you the energy inside R from R bar. And so in these cases, it is really true, even in the bulk, that you expect that the algebra will factorize as you expect also on the boundary. An example of how quantum mechanics is important, it's also related to what I said previously. Of course, if you go back to this correlator I was computing and you put back the factors of h bar and c, you will find that the factors look like h bar g by c cubed. In the limit where you come to classical gravity, this effect just goes away. So in the classical theory, you don't have holography. And also in the non-gravitational theory, if you take g to 0, you don't have holography. So of course, in these limits where you take the classical limit or the non-gravitational limit, these effects go away. Here's a more subtle case. It's related to some work done by Bahiru, Belin, Papadimos, Sarosi, Vardian a couple of years ago. And also more recent papers by Jensen and Witten, Jensen et al., Witten et al. You see, the point is that if you can ask how hard it is to distinguish some states. I gave you an example of a simple state. You can check, in fact, that if you have more complicated states with a high density of states around them, then distinguishing similar states, like distinguishing this heavy excitation from this heavy excitation with another ball here. If you squint your eyes, you can see there's a small excitation, small ball near the big ball. Distinguishing similar states requires a precision e to the minus s, where s controls the density of states. Now imagine that you coarse grain the observations outside. This is related to what we were discussing earlier with Nori. Imagine you tell the observer outside you only have some limited accuracy of observations. You can't measure things up to arbitrary precision. Then you can, in fact, hide information in that you can make it impossible for the observer outside to determine what is happening inside. And indeed, in this discussion of algebras corresponding to local regions in ADS, this is what is done. You introduce a heavy observer, and then you think of a set of small excitations about that heavy observer. And this is what allows you to get an algebra that effectively factorizes. So this process of introducing a background and coarse graining allows you to have effective factorization. Okay, now I want to spend the last 5 or 10 minutes discussing the implications of this case, of these results for black holes. Before that, are there any other questions about what I said? I can take them now, or I can go on to discussing black holes. Okay, so I'll assume there are no questions and go on to discuss black holes. So I want to discuss now the implications of what I said for the information paradox. Let me remind you what the information paradox is. Hawking found famously, now about 50 years ago, that if you think of a black hole, this is a picture of a black hole. This is Penrose diagram that I showed previously. And you vacuum fluctuations near the horizon of a black hole lead to radiation, and they lead to radiation that seemingly is uncorrelated with the details of the initial state. So it doesn't really depend on what the initial state was doing. Now, Hawking argued that since the radiation is uncorrelated with the initial state, you cannot, you can think of the following process where you have one star, you form a black hole, it leads to radiation. You take another star, it forms a second black hole, it leads to radiation. The two stars initially could have had different compositions. Maybe one had more hydrogen and less helium. The other had more helium or less hydrogen. However, Hawking's argument was since the radiation was uncorrelated with the initial state, you cannot reverse the time evolution arrows. And this, of course, would be in contradiction with unitarity, which is a very sacred principle in quantum mechanics. So this is the information paradox. Okay. Now, I want to say a little bit about the information paradox. Here's the first subtlety that one should realize. You see, Hawking's argument was that the process of Hawking radiation leads a pure state to evolve into a mixed state. However, let me emphasize that for the purposes of most observations, pure states and mixed states can be exponentially close to one another. This is a well-known result in statistical mechanics. And it simply says that, if we take the edge of our galaxy and we, disentangle it from the rest of the world, we'll now be in a pure state in our galaxy, as opposed to being in a mixed state, which is what we were earlier. However, most correlation functions basically won't change. They won't change to exponential accuracy. So it's a very physical result. And it tells you that pure states can be very close to exponential states. What this means in particular, however, is that to address the information paradox, we must allow a question of exponentially precise observations at infinity. If we decide that we are only coarse-grained observers and we do not have the ability to measure exponentially precise properties of the black hole, then we shouldn't be discussing the paradox at all, because at that order, if we coarse-grain our observations, then there's nothing to say about whether the state is pure or if it's mixed. Both of them look the same. So it's very important, that if we want to discuss the information paradox from the bulk, we have to allow the observer at infinity to make exponentially precise measurements. Why is this important? This is important because of what I've been saying so far. What I've been emphasizing so far is if you allow the set of observers outside to have information about all observations outside, then that tells you, these results have been tell you that information about the black hole microstate is always available outside with the correct measurements. And it never goes inside. So there's no loss of information. We can phrase this in a more precise way.
Suvrat, I don't want to disturb you. Just one quick.
Yeah.
But this is under the assumption, if I understand correctly, all of the correlator from the boundary to boundary. Am I right or not?
Yes.
Yeah. So that's a very strong statement, isn't it? All of the correlator.
You see, but if you don't know all of the correlators, you're guaranteed to lose information anyway.
But it come back. It come back, no? It come back in gen. Then you know. By the Hawking radiation, if you measure the Hawking radiation, the information.
Yeah, but you have to measure, you always have to measure all correlators in the Hawking radiation.
I agree.
So you
see, before the Hawking radiation come back,
yes,
something is behind the horizon, but all of the correlators. That's what you assume, right?
But you see, the point is that when the Hawking radiation comes, usually people say you measure all correlators in the Hawking radiation, so all fluctuation, but to accuracy e to the minus s.
That's I agree.
What I'm saying is that you could also measure all correlators before the Hawking radiation came, again to accuracy e to the minus s.
I see.
And you would still have
alternative way, you may say that. E to the s, actually, you can measure e to the s. Without the Hawking radiation, you can still detect. That's what you could.
Exactly. If you can measure e to the minus s, you don't have to wait for the Hawking radiation. In fact, there's no reason that it's easier to measure correlators in the Hawking radiation than it is to measure correlators.
Because you need e to the minus s precision.
Exactly. In both cases, you need e to the minus s. Exactly.
Okay.
Thank you.
Sorry. This statement is trivial for the ADS shifty. Is it?
Yeah, it's a subtle. I had a slide which I removed, unfortunately, on ADS-CFT. It's an interesting statement. I can explain to you a little bit more. The statement is the following. As you say, imagine a small black hole in ADS, which forms and evaporates. Okay. You can ask, does the difficulty of detecting this the information vary as you go along time? So when the black hole is present, it requires an accuracy e to the minus s to determine what the state of the black hole is. Okay. After the black hole has evaporated and you have Hawking radiation, naively, it requires a precision e to the minus s prime, where s prime is the entropy of the Hawking radiation, to determine the state. Okay. S prime actually is usually larger than s for a small black hole, because that's why the black hole evaporates, because the entropy is larger. Okay. So in fact, you might have thought that in ADS-CFT, if you take a small black hole, which are the kinds of black holes which evaporate, in fact, the difficulty of detecting the state becomes harder as you go forward with time. But this is a subtle question. We can discuss some subtleties about this later.
Okay.
Yes. Okay. Let me frame this argument in terms of the entanglement entropy. I know I'm running out of time, but I'll just take a few minutes more. You see, Hawking's arguments can be phrased as the statement that the entropy of the radiation, entropy of the state at null infinity from minus infinity to u, is always monotonically positive. This is a paradox, of course, because, if you start with a pure state, the entropy at scri plus should be the same as the entropy at scri minus. So sometimes you can say Hawking's argument is a statement the entropy should increase monotonically. This statement that I'm making is that the entropy of a segment of scri minus to u, in fact, is independent of u. And it's independent of u because you see all elements of the operator algebra are present near the pass boundary. And therefore, you don't expect to either lose or gain information, provided, of course, you keep track of all effects of e to the minus s. Okay, let me say this in another way. We could ask, what is really the error in Hawking's argument for information loss, right? Why are we getting a different result? So the first point I want to emphasize is that, the error in Hawking's argument is not, of course, in the computation of Hawking radiation, right? Hawking radiation is a perfectly valid computation, but it's a computation about low point observables. Now, as I said at the beginning, just knowing low point observables to order 1 accuracy is not sufficient to argue that you will get information loss. In fact, and this is something that's not realized, and when I started working on this, even I did not realize this, Hawking was aware of this problem. So if you actually open Hawking's paper on breakdown of predictability in gravitational collapse, and you see what the argument is, you will find Hawking is not saying, as is often said later, oh, we do a calculation of Hawking radiation and it looks thermal, and that's why the final state is mixed. Rather, Hawking had a more sophisticated argument. Hawking's argument was, if you look at a nice slice through the black hole, then the Hilbert space on the nice slice will factorize into the space outside and the space inside. That's what he's calling H2 and H3. On the left-hand side, I really have a screenshot from Hawking's paper. And he said, the observer outside has to trace over the space of data inside. That's what he called the principle of ignorance. If you open his paper, this was very important for him. And so his argument was, even if the form of Hawking radiation was corrected, the causal properties of the space-time tell you that the observer outside is space-like separated from what's happening inside, and therefore must trace over everything inside, subject to a few constraints which are imposed by the Noether theorem. So he also accounted for the fact that the Noether theorem tells you can measure the mass, charge, and angular momentum at infinity. And he said, subject to that, you have to trace over what's happening inside. However, the discussion I've been giving you so far is that the Noether theorem is a classical theorem, but if you impose also correctly quantum mechanical constraints, then you find that it's not just the mass, charge, and angular momentum, but rather all information you can measure outside. So if one were to say, where is the error in Hawking's argument? I think it's clear that the error is here in this set of paragraphs. You can point precisely to where the error is. And the error is that Hawking assumed that you had the Noether theorem and it would be true in the theory of quantum gravity. But that's demonstrably false once you include both results of gravity and quantum mechanics, provided you make the right assumptions, as I said about the UV complete theory. I should also say that this picture I'm presenting is slightly different also from the conventional picture of the page curve, which is the idea that the entropy of the region outside should first go up according to Hawking's calculation and then come down. Okay? And that's because if you look at the derivation of the page curve, that also assumes factorization. So the page curve is correct in a non-gravitational theory when you can factorize a Hilbert space. But if you look at its assumption for a black hole background, that also assumes factorization. Now, that doesn't mean that you can never find a page curve. Of course, there have been many calculations of the page curve in theories of gravity. I'll say a little bit more about those below. But in a standard theory of gravity, if you keep track of all observables and look at the state outside, that entropy, I think, does not follow a page curve. Let me, in the last 2 minutes, now explain which entropies do follow a page curve, because this has been such an active area of research recently. So, of course, there have been many computations of the page curve for black holes in recent years, but these do not contradict our results. In particular, let me remind you how these calculations are done. This is a cartoon of how these calculations are done. You take a theory of gravity in this blue region with a black hole in the middle, that's this region here, and then you have this non-gravitational bath, that is the region, the pink region outside. In the non-gravitational bath, you make an imaginary interface in this dashed region, and then you ask for the entanglement entropy of one region with the other region. Let me emphasize that gravity in this setup is not dynamical throughout space. Rather, these models always involve a non-gravitational bath. In such a picture, you can in fact replace the entire gravitational region inside with some degrees of freedom on the boundary, so that on the right-hand side, you have a picture of what is called a BCFT, which means a CFT with a boundary. Okay? So this entire system is a non-gravitational system. In this non-gravitational system, you have two regions, and then you can ask for what is the information transfer between these non-gravitating subregions. And of course, if you do that, you get the page curve. And I think these calculations are very nice because they tell you how in this BCFT you can compute the entropy in the BCFT using a gravitational path integral calculation. The only objection I would have is that I would say this is not the page curve of Hawking radiation. I would rather use the phrase, this is the page curve of one part of the BCFT with another part, but that's a question of terminology. So just to say, there's no contradiction between what I said and these calculations. It's more a question of what are the phrase you use, to give names to what you computed. Okay. In fact, this picture that I presented is also useful because it helps to answer some objections that have been raised to these computations of the page curve. If you look at these computations that use the island proposal, for instance, Martinek and Mathur objected and they said, how did information enter the bath from the black hole? It couldn't have jumped. But let me remind you that, what I've been telling you is that information in a gravitational theory is always present near the boundary of the theory. So now think of this process as a two-step process. First, where you have just a black hole in a gravitational region. In this setup, the information is already present near the boundary according to what I said. And then you add on a bath in the second step. When you do that, information just flows from the boundary into this. So it does not have to jump from inside the black hole to the bath. Rather, it's just information that's present already in the gravitational degrees of freedom near the boundary that flows into the bath. So in fact, it also helps to give a picture for how information is entering the bath in these computations with the island proposal. Okay? So not only is there no contradiction, I think thinking about the holography of information helps understand why these computations work. Okay, so I'm done. Let me just summarize. The main point of this talk was to say that standard theories of gravity store quantum information very differently from local quantum field theories. In the end, this is a non-perturbative result, but it relies on some assumptions about the UV complete theory, which we think are weak assumptions, but they're specific assumptions you need to make. It is not just a formal result. For simple states, it can be verified in perturbation theory. I think it helps to explain why gravitational theories are holographic. Accounting for this unusual localization of information, I think it helps to understand paradoxes about black holes. Conversely, forgetting about it helps to generate paradoxes about black holes. Recent computations of the page curve, they involve a non-gravitational bath. In these settings, the Hilbert space does factorize. And so, you're back in a setting where information is localized like an ordinary quantum field theory. However, holography of information also helps to understand in these setups how information enters the bath. Okay, so that's all I wanted to say. Thank you very much for your attention. I'll stop here.
Okay, thank you very much for the beautiful lecture. Okay, let's thank to the Suvrat. Okay, so time for question. So if you have a question, just unmute and please speak.
Can I ask a question, Suvrat?
Yes, please.
Thank you very much. Very beautiful talk. And I have a question about this localization of information, as you talked about in this colloquium. And you said, I think, as long as we're looking everything in classically, this localization cannot be seen.
Correct, yes.
So why this quantumness is so important? Of course, you gave a proof. So roughly, but what do you think the most essential part?
I think the most essential part was the uncertainty principle. It was really the fact that, what we were exploiting was that if you take an energy eigenstate, the energy eigenstate cannot really be localized in a theory of quantum mechanics. So you can think of this process of getting information from infinity in a two-step process. First, say you measure the energy. Then you have, after you measure the energy, say you have projected down to an energy eigenstate, there might then be still many energy eigenstates at that level. But you can, if you measure other observables in a quantum mechanical theory, you can always distinguish between different energy eigenstates because energy eigenstates can never be strictly localized. So it's really the uncertainty principle, I think, that's important. That does not hold true in a classical theory. I mean, it's very easy to see counterexamples. So let me say it another way. Imagine that you have two balls. One of them is a dense ball, and the other is a dilute ball of dust. Now, by Birkhoff's theorem, if you just measure the gravitational field and they have the same mass, imagine they're spherically symmetric. If you just measure H, then of course H is the same for both the balls, right? So the picture I have in mind is, you have two balls. They have the same mass, so H is equal to H here. But now think of the uncertainty principle. Can you see this figure that I'm drawing?
Yeah.
Now, sorry, in a quantum mechanical theory, this ball you would have to make by superposing a larger number of energy eigenstates because it's a more dense ball. So if you think how you will generate it, and whereas on the left-hand side, you superpose a smaller number of energy eigenstates. So in a quantum mechanical theory, h squared here is greater than h squared on the right-hand side. So, but you see, in the classical theory, h squared is the same as h squared, right? Classically, you don't see this difference. Classically, h squared is equal to h squared. So the fact that there is to make an excitation or make a state, you have to superpose different energy eigenstates is very crucial, and that's only true in quantum mechanics. And that's why it's only in quantum mechanics that you can see you can differentiate between these two balls, but not in the classical theory. Right?
I see. Yeah, thank you. I see. So this fluctuation is quite important.
Yes.
Thank you very much. Yeah.
Thank you.
Other question, please?
Sorry, could you explain again about the effective factorization of the Hilbert space? What condition it effectively factorizes do you create?
Yeah. So I gave several different cases. Let me just go back to that, please. 1 second, please. Let me erase these drawings. I'm not sure which it was. Yeah. So you see, this is one case, of course, when the Hilbert space just exactly factorizes. This is the case where we study in the Ryu-Takenagi formula, which is you have a region R and a region R bar, and then there is no there's no Gauss law. Of course, you can't measure the energy of R from R bar, and the Hilbert space factorizes. This is one case where both.
So here you assume that it's a free gravity theory.
It can be an interacting gravitational theory. You see, this is the case we have in ADS-CFT, right? Because
but it is the bulk side. It's just a gravity theory.
In the bulk side, it's just a gravity theory. Yes.
As you said, so it's a bulk side. It should be not factorized. That's
no, I don't think so. In fact, if you include a small buffer region, this is the region that we have here, then the constraints, you see, the reason it's factorized, you can have separate states is because you can think of an excitation in the region on this, which you can dress to infinity. You can make the gravitational Wilson line go off to this part, and you think of an excitation here, and you make the gravitational Wilson line go off to that part. And so there are operators that belong to R and R bar that commute exactly. Of course, from entanglement wedge reconstruction, we expect this to be true because we expect that the region R is dual to the green region on the boundary, and the region R bar is dual to the blue region.
Okay, but we can consider the we can consider some gravitational lines across the horizon.
Yes. So we can consider. What I want to say is that you can have the split property in that there are some. I'm not saying that. You see, of course, there are some operators that belong to both R and R bar. What I'm saying is that you can write down now operators that belong purely to R, and some operators that belong purely to R bar. So if you have some information in R, you can hide it from R bar. There are observables in R which commute completely with observables in R bar. The point I was trying to make was in other setups, there is no observable that belongs purely to a bounded region. You can always determine from outside what's happening. In this setup, you cannot determine the information in R from R bar.
Okay, so here you can, this epsilon, this is a strict, you remove such region strictly, so there is no operator on that region. That is what your assumption. Okay.
This is always required. Even in a non-gravitational theory, you need a small buffer region. So that you have to separate, because even in a non-gravitational theory, the Hilbert space doesn't factor.
With the shift or in general, if you have some strict, a blank region, then it should be factored. It's obvious. That's what you said.
Yes.
Okay. I see. Thank you very much.
I also gave some other examples of effective factorization.
Usually flux go all the way, is that right?
Yes,
So
but you can.
gravitational addressing localized in one region, I think it's impossible, isn't it, or not?
I don't think it's impossible. In this case, in fact, it's clear it is possible, right? Because you see, let's say
if you make the gravitational flux dressing in one region, yes, I agree, it's factorized. But usually it's spread all the way.
Yes. So you can
write down local operator, it's spread both R and R bar region. Is that right?
You can write down some operators that are not factorized, that don't belong to R or to R bar.
Yes.
But I want to prove a weaker result. I just want to say there are some operators that belong to R that commute exactly
some
with
operator
operators
you can
in
do, but you are not claiming all those operators can factorize in this way.
No, clearly there are some operators you can draw which are just non-local operators, which are like where you have a Wilson line that goes from here to here. So there are some operators which don't belong to R and R bar, but that's also true in a non-gravitational theory, right? There are some operators that belong to both regions.
Okay.
If you have, so this is not, the split property is always a statement that there is a set of operators you can associate with one region and another with another region, and they commute exactly.
Okay.
So in this case, gravity behaves like a quantum field theory. I gave some other examples. Maybe this was also an interesting example where the Hilbert space effectively factorizes. This arises from coarse graining. Here I said, if you think of a heavy background state, and then you think of some other small excitation about that background, and you coarse grain the observer outside, then they cannot distinguish what's happening inside. So this is another example of where these effects are not important.
Okay, so thank you very much.
Thank you. Yeah.
So can I ask a question?
Yeah, sure. Yeah.
So you showed us some steps for the proof, and in the second step, maybe I think. Could you show the slide?
Yeah, I'll just show slide 1 second, please. Sorry. Here, right? Somewhere here. Yeah.
Yes, this slide. So in this second step, can I think it as a Reach leader theorem?
Yes. It's a weak version of the Reach leader theorem. It's a weak version because I only needed the positivity of the Hamiltonian. Usually the Reach leader theorem is proved using the spectrum condition in quantum field theory. This is a weak version because I'm allowing my operators to be smeared all over this sphere. And I emphasize, we are not assuming it. You can prove it based on the assumption that the Hamiltonian is bounded below for the algebra on null infinity.
I see. Thank you.
Yeah. The Reach leader theorem is usually stated for any open set in the bulk of a quantum field theory. And of course, that's not true in gravity because of the discussion we had. But at asymptotic infinity, if you think of a subregion based on the positivity of the Hamiltonian, you can prove it also for a theory of gravity. It is the Reach leader theorem, as you said, a weak version of it. Yeah.
Okay. Thank you.
Thank you. Yeah.
Any other question, please? No? Okay, if not, then let's thank to the Suvrat for the beautiful colloquium talk. Thank you very much.